So if you've reached a point in your matrix work where you start to consider things like eigenvalues and eigenvectors, it might be worth considering first of all matrix powers and how these work, and then how they relate to eigenvectors and eigenvalues, and where we go from there. So I think this is a nice introduction before we start looking at eigenvalues and eigenvectors. First of all, we're going to look at matrix powers of diagonal matrices. What's a diagonal matrix? A diagonal matrix is a matrix that has only entries in the diagonal positions from top left to bottom right. So the identity matrix is a diagonal matrix. It only has an entry in top left and bottom right along this diagonal. Okay, and the other entries are 0, and that is what defines a diagonal matrix. So we'll first of all look at the square of the identity matrix, which you may have considered before, but of course that looks a bit like this: 1, 0, 0, 1 multiplied by 1, 0, 0, 1, and we simply use rules of matrices. So that row times that column, so 1 times 1 plus 0 times 0 in the top left position, 1 times 0 plus 0 times 1 in this position. I should have put 0 times 0 there, I suppose. 0 times 1 plus 1 times 0 in bottom left, and 0 times 0 plus 1 times 1 in the bottom right position. And no surprises, the identity matrix squared is 1, 0, 0, 1. So it's almost like the matrix equivalent of just 1 times 1 is 1. There it is. So that's the power of the identity matrix. So let's move down and look at a matrix that's not an identity matrix, but is still a diagonal matrix. It's still got that pattern where there's only non-zero entries in the diagonal from top left to bottom right. The other entries are all 0. And I must also say we're just considering 2 by 2 matrices in this video, but this can be expanded to larger matrices. So let's have a look at what this one looks like. 3, 0, 0, 1 multiplied by itself. 0, 1. Let's use just our matrix methods again. I'll go down here, so it didn't seem to be too much space up there before. So let's have a look. Again, this right now, I'll just do maybe a highlighter markup pen just to remind you of what I'm doing here. This is the way matrix multiplication works. So it's this row times this column. Okay, so it's rows and columns, isn't it? Rows and columns. Here we go. So 3 times 3 plus 0 times 0 in the top left position. Top right would be this row times this column. So that would be 3 times 0 plus 0 times 1. And then bottom left position would be this row times this column. So 0 times 3 plus 1 times 0. And finally, we'd have bottom row times the column on the right. 0 times 0 plus 1 times 1. And what do we end up with? Let's have a look. Intuitively, you may have made this step already. 3 times 3 plus 0 times 0 is 9. 3 times 0 is 0 times 1, that's 0. 0 times 3, 1 times 0, 0. And we get a 1. And intuitively, you may have made that step already. But yeah, 9001. So this diagonal matrix squared gives us that result. Now we're only looking at diagonal matrices in this video, and you'll find out why, and you'll realize why when you study eigenvectors and eigenvalues and how we use them to find matrix powers by diagonalizing a matrix. But I think it's some nice results to know before we start doing that and thinking, well, might be the reason why. We can extend that further now. Now it's a matrix cubed. Let's see where we go with this. Well, first of all, we've got to square the matrix. So we've got this going on here. Now, intuitively, we think it's going to be 4 cubed and negative 2 cubed in those diagonal positions, but it's nice to check, just double check. So first of all, let's do let's just do 4, 0, 0, negative 2 multiplied by 4, 0, 0, negative 2. I'll probably skip out some working now because I think I've just shown you up the top there what we're doing. So 4 4s are 16 plus 0, that is 16. 4 zeros and 0 negative 2s is 0. 0 4s and negative 2 zeros is 0. And negative 2 times, 0 times 0, negative 2 times negative 2 is positive 4. And then, so skipping a bit of that multiplication working, but I think we're multiplying and adding, and you're studying matrices, you probably will be able to do that working in your head. Let's just confirm that. 16 4s plus 0 negative 2s, yes, that's 64. 16 zeros plus 0 times negative 2, 0 4s and 4 zeros, and 0 zeros and 4 negative 2s, negative 8. And yes, intuitively we think, oh wow, that is confirmed. That's a nice confirmation of what we thought was going to happen. So, bearing in mind, these are diagonal matrices only. They're not matrices that have entries in these positions. There's 0 entries everywhere apart from the diagonal from top left to bottom right. And we get these lovely results. And you can see why, because we get these 4 zeros and 0 negative 2s. You're always adding together products of a product which includes a 0. So we'll have a look now at generalizing. We think this is going to be k cubed, k cubed. We can actually just show this one, can't we? We could actually just, well, let's have a look. It's k0, 0, k squared times, k0, 0, k. Well, k0, 0, k squared is equal to, yeah. Oh dear, I've made a bit of a mistake there, haven't I? Whoops. Let's just quickly go back there. I don't know what came over me there. K0, 0, k. We get k squared, we get 0, we get 0, and we get k squared, absolutely. And then you can see why this happens once you start working this through. And you do get, yes, as we expected, k squared times k cubed plus 0, whoops, k squared times 0, 0 times k, that's a 0, 0 times k, and k squared times 0, that's a 0, and 0 times 0, that's a k cubed. So we do get the result we expected. And that kind of intuitive step we think is going to happen at this point. And I suppose at this point we could, because that's going to be true for any value of k, whether k is positive or negative. I should also say k is a fraction. I didn't do a fraction example, but k could be a half or a third, any fraction, any quotient. You could put it in there, and that's going to be true for all values of k. So at this point, we're probably wondering, well, I wonder if this is true for all values. And we can have a really good think about that now, and probably do an informal proof. Some courses require knowledge of proof by a thing called induction. Some courses don't, but we can have a little go at informally doing it now, or maybe even formally. Well, when we let's consider this, and I've used k in the matrix positions, but for induction, you're probably not used to using k in there. So I use a in here now for these entries into the diagonal square matrix. It's just a 2 by 2 for now, but we will try and work out what this looks like. Okay, we think we know it's going to be. We're going to try to prove that the result is a to the power n in these diagonal positions. So let's try it for n is 1. Well, we know that's true because, oh no, sorry, I should put there. Is this equal to a to the n 0, 0, a to the n? That's what we're going to try and prove for all values of a and n. So it's an identity there. Let's try it. When n is 1, what have we got? We've got a 0, 0, a is equal to a to the power 1, 0, 0, a to the power 1. So that's true, isn't it? That's absolutely true. So we can accept that. We're going to assume it's true now for n is k. Assume true for n is k. This is how our proof by induction works. So this is an assumption that, apologies, I didn't put my power 1 there, did I? A bit naughty. So a 0, 0, a to the power k is equal to a to the power k 0, 0, a to the power k. That's a presumption it's true. And then we've got to prove it's true. To prove it's true, true for n equals k plus 1. So let's try that now. So we're going to consider now a 0, 0, a to the power k plus 1. I'm going to try and show that that's equal to a to the power k plus 1 in the diagonal positions of the matrix. So how do we do it? Well, we know that that's got to be equal to a 0, 0, a to the power k multiplied by, oopsie-daisy, multiplied by a 0, 0, a to the power 1. But we've just made an assumption above that a 0, this is our assumption I can directly use now. And I can directly use that assumption. Here, you see, I can make a substitution that a 0, 0, a to the power k is a to the k 0, 0, a to the k. That's an assumption I've made. This is how proof by induction works for those of you who've seen it before. If you've not seen it before, oops, what's going on here? Let's just try and do that. There we go. A little bit of a hiccup there in the IT. Okay, so I'm going to make that assumption now. So I know that there is my assumption from above. So that's a to the power k, 0, 0, a to the power k, multiplied now by a 0, 0, a. And then what can I do now? Well, my multiplication of matrices, I know how to do this. What is it? A to the power k times a plus 0 times a. A to the power k times a plus 0 times a. Top right position, a to the power k times 0 plus 0 times a. And we've got used to that in the previous examples that we're getting these negatives, negative 0 plus another 0. That's why these diagonal matrices work in this way. Here we get 0 times a plus a to the k times 0, similar thing. And lastly, we get 0 times 0 plus a to the k times a. And of course, rules of indices from our kind of years gone by. A to the power k times a is a to the power k plus 1. That's 0, that's 0, and that's a to the power k plus 1. And we have shown that a, let's mark it up for you. We have just shown that a to the power a0, 0, a to the power k plus 1 is indeed equal to the final thing there. And that is a proof by induction. And you can say, therefore, proof by induction. Or you can say QED if you're posh, or Bob's your uncle if you're not. Okay, so what have we learned today? We've learned that if we've got a diagonal matrix, I've only shown you for 2x2s, but diagonal matrix, that's matrices with with entries only in the top left diagonal, top left to bottom right diagonal, with other entries 0. The powers can be calculated very straightforwardly. And it's just the powers of the entries. Okay, thanks very much, and hopefully we'll be moving on soon to working out why this is important and why this is an important step in matrices. Thanks. Bye-bye.